So this is joint with Fedor Sandomierski and Joe Root. Here we are hard at work. Three of us have actually never been in the same room together. This is all a pandemic project. So in this project, we're interested in matching with aligned preferences. Let me explain what this is. So here's an example. So you have, so it's two-sided matching, two populations, X and Y. And we form couples, one agent from X, one agent from Y. And the utility that they get is the same. So if X1 and Y1 form a couple, from a pair, then the utility that X1 gets and the utility that Y1 gets are the same. So here's an example where I put the utilities as a matrix. So if X1 forms a pair with Y3, then both of them get utility 8. So imagine you want to find the stable matchings. It's pretty obvious that X1 and Y3 has to be together, otherwise they form a blocking pair. So once I realize that, I form that couple, and I take them out of the economy, and I'm left with X2, X3 and Y1, Y2, and then it's clear that X3 and Y3 have to form a pair, otherwise they will block, right? And so on. Okay, so this gives me a very simple way of understanding what the stable matchings have to be in this type of simple environment. Okay, so this is a type of structure and preferences that I have a sense people don't think is particularly interesting. So I want to tell you you're wrong if you think that. It is more interesting than you think. And we're actually not the first ones to notice this. It's a paper that's actually been around for a while that Ferdowsian, Niederle, and Yariv wrote, which studies this type of models with aligned preferences. So if you are curious, suppose instead what you try to do is you look at the utilitarian sum of utilities, which is what you would do if this were an assignment problem. Then you would match along the diagonals because that gives you higher utilitarian welfare. This is clearly not what stability gives you. So one question you might be interested in is what is the connection between these two objects? And we'll have something to say about that. Okay, so let me show you another example to convince you that this is indeed an interesting type of structure. So here's the example. So I'm going to look at, in this example, at infinite matching markets. Imagine you have two populations of agents, and the two populations, they are described by a number on the real line. And so one of them will be represented by one measure mu on X, which is a subset of the real line, and another population is nu, and let's say they both have a density. Now, the utility from a match will be how close people are to each other. So let's imagine that each agent is described by this position on the line, and like wants to be with like, so people want to be with people who are as similar to them as possible. Okay, so very simple preferences. So here's an example. I have two densities, the red density and the blue density, and they happen to have this joint support in this example. All right. So what do the stable matchings look like here? I'll give you a few seconds to think about it. People want to be with people who are very similar to them. So I'll show you a picture. So I took away the colors and I put what was it? Blue. So the blue ones I put pointing down just to make it easier to see. Okay, same densities, but I just put one density pointing up, the other one pointing down. Okay. So if you think about the example I showed you before, where there was a number 8, and it was obvious that the people that generated 8 had to be together, here you see that the people who are very, very, who can be very close to each other, they have to be, match to each other. Otherwise, they will block. Right? So what's going to happen is that I'm going to match these guys together, and these guys together, and then I'm going to sort of imagine if you could do this sequentially. Then I'm going to start to sort of move out and form couples that are, further and further away from each other. Right? So I'm going to start matching these guys to each other and move out all the time. The same with the blue ones, the same with these green couples, except here, the speed, because these densities have different heights, in any given interval, there are more of these guys than there are of these guys. So therefore, I'm gonna, the the speed at which I move to the right here is faster. You can imagine that. So after a while, it's going to look like this. I'm going to exhaust these guys. I'm going to reach the midpoint in which these are going to be matched with these. And also some of these are going to be matched over here. And then I'm going to be left with this leftovers that this sort of greedy algorithm couldn't handle anymore. And then I would start to have to match people who are very far away from each other. So this is what the stable matchings will look like, these arcs. And so hopefully you think, well, that's actually pretty cool. I didn't think that it could be this interesting. It's actually a structural property that we call no crossing. So if you see none of these arcs cross each other. And this turns out to be a general property whenever you're thinking about matching on the real line like we're doing here. And that's sort of part of what I try to convince you that this is, if you think about these matching markets and you think about them through the lens of optimal transport, which is what we've seen in a moment, there are structural properties of the stable matchings, which we can study in this way, and that are interesting to learn and to understand. Here's another example, just to show you the difference between stability and fairness. It's a very, very simple example. You have this density and this density. Again, stability will match these guys to each other, and then when I start to move out, I get these arcs. But this is very unfair, right? Because these people get very high utility. They're matched closely to each other. These people here are miserable. They are matched to agents who are very different from them. But I could make everyone just as happy keeping the distance between any pair constant by matching them in this way. So if you want stability, this is what you get. If you want to be fair, this is what you get.
There's something, sorry, Federico.
Yeah.
So this is the knife edge case, right? It's very well known in optimal transport. You take L1 distance. If you do the utilitarian solution to take your vocabulary, you get two optimal outcomes, right? So the two you showed are both optimal. This is the one knife edge case in which there's no uniqueness.
No. I know what you mean. Let's talk about optimal later. I don't know what you mean by optimal. But they will have two different. Give me a bit more time. I'll show you what we. Anyway, so quick overview of what we do in the paper. So first of all, align preferences. I'm going to argue are interesting. They emerge naturally in some problems. For example, when there is an objective notion of fit. So two agents get the same utility, maybe because there's some natural way in which we talk about match quality, and then both sides care about this match quality. It could be, for example, you're thinking about something like organ donations or something like that. You care about how good of a fit is this donor for this patient and things like that. Then there is this objective notion that is driving the preferences. Also matching with transfers, like the ones that Bernard was talking about earlier today. So in matching with transfers, you imagine that when the agents are bargaining, they're also bargaining over transfers. Also, for example, in the marriage application, you imagine that when you're bargaining over, who's going to be your partner, you're also bargaining with them about the transfers. But you might imagine many situations in which you can't commit to a transfer at the point at which you're bargaining. After you got married, then you can't sort of there's no contract that says who's going to do the dishes, who's going to and so if that happens, then you can think that every pair has sort of backward inducts what the outcome of the internal bargaining will be, and then you naturally get this type of common. Another reason we think this is interesting is what I'll show you next, which is the connection to optimal transport, which shows that these ideas of stability that and also fairness that are naturally connected to some optimization problems, at least in an approximate sense. And so we can study them through the lens of optimal transport, and that will give you some insight. For example, these structural properties of stable matchings that I was mentioning before. There will be a tension between stability and fairness that we will see emerge from this optimal transport. I will be able to talk about approximate utilitarian welfare maximization, which is maybe what Bernard is thinking about, but here the objective will actually be different from the ones here. So you will see this in a minute. Another thing that we think is really important is that these results extend beyond the two-sided matching problem to the many-sided matching problems, in which existence is generally not guaranteed. So there's sort of man, woman, child problem, which is known to have non-existence of stable matching. But under the assumption of aligned preferences, then stability does exist, and many of our results extend to these settings, and then it allows us to capture problems like, for example, team formation, supply chains problems. Also, you can encode certain organ donation problem in this type of setting. So I won't have time to talk about that today, but when the paper is written, that will be still a bit of time. We'll get there. Okay, so this is the model. Like you saw in the examples, I will be interested in markets which are not necessarily finite. So one advantage of this is that we can talk about very general matching markets, and in particular, we can talk about matching markets that are not necessarily finite. So a matching problem is a tuple x mu y nu u and v, where x and y are Polish spaces. So these are complete measurizable, separable spaces with a natural measurability structure. Mu will be some measure which is finite on x, and the nu is another finite measure on nu. And in fact, the measure on the two are the same. So this should be a nu, not a mu. Okay. And then u and v are two functions, which are going to be the two utility functions. Right? Any questions about the model? No. So, for example, an example of this is the example that I was showing you about before, where you have the agents were situated on the real line, and you have some density that describes the two populations. That's one example. Okay, so what's a matching? A matching is a finite measure on the product space, which respects the two marginals. So if I look at the marginal on x, it's equal to mu, and the marginal on y is equal to mu. That's a matching. And pi of mu nu is the set of all matchings. Stability. What does stability mean? So matching pi is epsilon stable. I'm going to work with approximations throughout here. If when I draw a couple, x1, y1, and then independently draw another couple, x2, y2, according to the matching. Okay, so x1 and y1 are, in a sense, matched in pi. And x2 and y2 are, in a sense, matched in pi. Okay, I draw two couples according to this pi, and I draw them independently. And then I take the x component of y and the y component of the other, and I check whether they form a blocking pair. Okay, and then what would it mean for it to be a blocking pair? Where it would mean that this mismatch is higher than, so x1 gets higher utility here with y2 than with y1, and y2 gets higher utility here than what they get with x. Okay, so if at least one of these holds, and I have an epsilon that goes in my favor here. Okay, so hopefully this looks familiar enough that you believe that in this potentially infinite world, this is a reasonable notion of stability matches. Okay, so this is the definition of stability. However, if you don't like it, I have an equivalent one. This one requires U and V to be continuous. So if they are continuous functions, then a matching is epsilon stable. If when I take two couples in the support of pi, then if I mix match them, then they don't want to block. Okay, this little lemma shows that the two things are equivalent. Okay. Anyway, hopefully this makes sense as the natural notion of stability. All right. So I'm going to focus on aligned preferences. So what does it mean for preferences to be aligned? Well, they're aligned if the utilities are the same. Utility, if U and V are the same. Right. In that case, this inequality simplify, and a matching is stable if whenever I take the two couples, x1 and y1 and x2 and y2, the inequality, the utility of the mismatched, of the potential blocking pair doesn't exceed the largest of these two. Right? If it were to be bigger, then x1 would want to block and y2 would want to block. Because the utility that x1 gets is described by u. So this utility will be higher than what x1 gets with y1. And at the same time, the utility y2 gets, which is also described by u in this case because of the aligned preferences, is higher than what y2 gets when they're matched with x2. Okay. So with aligned preferences, the stability requirements collapse to this inequality. Okay, a little bit simpler. All right. Okay, that's stability. What about egalitarianism? I want to get at fairness as well as stability. So here's what we mean by being when we want to be fair. So for each matching, I can look at the smallest utility that a couple gets in the matching, okay? So the least utility in the support of pi. All right. And if this minimum doesn't exist, I can replace it with an infimum. That's okay. Okay. So this is the least utility that a sort of matched couple gets. Okay. Matching is egalitarian if it maximizes this objective. If it maximizes the smallest utility at any moment in the support of the matching. And again, we need to relax things. So I will say it's epsilon delta egalitarian if there is a subset S of couples which has probability at least 1 minus delta, such that everyone in that set is getting utility at least the minimum possible, the one that solves this problem, minus epsilon. Okay, so if I solve this problem, that's pi star, then I give myself an epsilon. Everyone in S gets at least that much utility. And the set S is large in the sense that it has probability at least 1 minus delta. That's what epsilon delta is. Okay, that's epsilon delta egalitarian. All right, so we know what stability means. We know what it means to be egalitarian. All right, so I'm going to claim that this has a connection to optimal transport. So what is optimal transport? So it's this. It's a sort of a theory that's a special case of linear programming that has been studied a lot and which focuses on matchings. So if a function C that maps x cross y into R is called a cost function, then the optimal transport problem that is associated to C and to the two populations mu and nu is a problem of finding a matching that minimizes cost. Okay. It minimizes the cost of any couple that I form. Now, I want to come up with a particular cost function that I think will end up, hopefully you'll see, end up making sense. It might not be what you expect. There's something slightly funny about it, but it does true. So consider this cost function. So the cost associated to x and y is 1 over alpha times 1 minus e to the alpha times u. Okay. So this might look strange, but if you think about it for a minute, it maybe starts to make sense. So think first about the case, what happens when alpha is positive? Remember, we're going to be studying this optimal transport problem that minimizes cost. So when alpha is positive, I'm minimizing cost, and this is the cost of x and y. So when alpha is positive, I can ignore alpha, take it out of here. I'm still minimizing what's left. And this 1 is a constant. I can forget about that. And there's a minus in front of it. But then a minus in front of a minimization problem turns it into a maximization problem. So you can think about this problem then as about maximizing e to the alpha u. But that's like maximizing a convex function of u. But taking alpha to be large, I can make it very convex. Right. Okay, so that's what happens when alpha is positive and large. Now imagine I take alpha to be negative. When alpha is negative, again, keep in mind it's negative and take it out. Now throw away the 1 again, which is now a minus 1, never mind, take it out. But now this minus became a plus because it was negative. So now I'm minimizing this thing. But I'm more comfortable thinking about maximum. We just talked about maximum. So let's put the minus back and turn the min into a max. Then what are we doing? We're maximizing again, minus e to the alpha u, where alpha is negative. So now I'm maximizing a concave function of u. And then I'm going to make this very concave, but taking the alpha to be larger. So that's what this is trying to do. And it actually, this particular functional form doesn't matter. There's a way of generalizing this, which I might mention later. Okay, so then we get these two theorems. So remember, the optimal transport problem is the one here, and minimizing cost. And then I have these two theorems, one for stability, one for fairness. When alpha is positive, any solution to this optimal transport problem will be epsilon stable, when epsilon is log 2 over alpha. Okay, so by taking alpha positive and large enough, I can get the stability requirement to be tight. Okay, I can make the epsilon to be small. All right. Why does this make sense? Well, remember, this corresponds to maximizing this function that are going to make it be very convex. And think about this idea in the example I talked about in the beginning, where we started by worrying about these guys that generated a lot of utility, the 8 in the matrix. So by making this objective be very, very convex, we're going to make sure that we put a lot of weight on those very high utility generating couples. Okay, so that's a rough intuition for why this generates epsilon stable magic. On the contrary, if we look at negative alphas, then any solution will be epsilon delta egalitarian, where for any epsilon, I can make the delta small enough by taking the alpha to be very, very big. Okay. And remember that the delta, so the probability of S, which was all the people who were guaranteeing a certain minimal level of utility to, was 1 minus delta. Okay. So by making delta small, I'm making sure that we're guaranteeing this level of utility to a lot of people. Okay. Yeah, and it doesn't, yeah, so you can generalize this to other cost function, doesn't need to be the one that I show you. All right, so there is an interest in the existence of stable matchings in infinite markets, so we can get that as a corollary. So if you look at, if you look at all the solutions to the transportation problem with positive alpha, and you take a sequence of solutions as alpha goes to infinity, and you collect here all the limit points of this way of proceeding. This actually, by the way, even though x and y may not be compact, there's enough compactness in here, in the optimal transport problem, due to the fact that the marginals are fixed. That this type of thing makes sense. So, for example, you can get existence of optimal transport problems even without assuming compactness. So if I take my U and I reparameterize it to make sure it's bounded, which you can do in standard ways, and then you look at this set of limit points. It is a non-empty, convex. It's a weakly closed set of stable matchings. So this gives us existence, and it gives us a way of, in some sense, finding stable matchings for this problem. And I guess I don't have. Okay, so let me tell you this. I was hoping to show you a little bit of a proof. Okay, so let me tell you about the connection with utilitarianism. And let me just state the result. Maybe this is what Bernard had in mind. So if you're looking at the utilitarian welfare of the maxim of a matching, and you look at the problem of maximizing utilitarian welfare, then actually any epsilon stable matching satisfies this welfare guarantee that I can achieve at least 1/2 of the optimal utilitarian.
How does are they comparable stable matchings and egalitarian? I mean, a stable matching can be the most non-egalitarian matching. Is it the most non-egalitarian matching in some sense? We're using the worst.
That's a good question. I'm sure you can generate stable matchings which are very unfair. You can maybe get them to be as unfair as you want.
But in your setup, I have the feeling that they might be the most non-egalitarian too, right? Because of assortative matching.
I don't know what you mean by assortative.
Everybody likes the likes of them.
Yes,
Anyway, you can talk later.
Yeah, I mean that's true in the example I showed in the beginning. But in general, there's no notion of people being similar to each other. So in my model, the spaces x and y, there's no reason why it makes sense of comparing how similar people are to each other.
Give a simple example. Everybody might have a productivity number, and the total product is the multiplication of the both.
Yeah. So I mean, for sure you can create examples which are where this becomes assortative, but in general this has no connection to assortativeness. There's no, but there is though a structural property that is relevant, which is that actually makes sense in our setting. Maybe I would mention that. So this is a very standard idea in optimal transport in other areas, which is cyclic monotonicity. So even though I can't compare x and y, I can talk about the cost of x and y. So a subset of the product x and y is called cyclically monotone if I form sequences of pairs and I look at the sum of the cost of the pairs. Okay, and I shift one of the elements of the pair by one, and I pick the pair so that this is so the summation is sort of mod m, no? So that yn plus 1 equals y1. Then this inequality has to hold. Okay? You may be familiar with this notion of cyclic monotonicity. It shows up in mechanism design, many other settings. convex analysis is very important. But this property of cyclic monotonicity is true of the support of any solution to the optimal transfer problem, let's say. So any solution of the optimal transfer problem has to be supported in a cyclically monotone set. And this is a structural property that we can talk about. So this is where the no crossing property comes from in the one-dimensional set. And then, yeah, I'm out of time. So I'll skip the proof. And, maybe I will just mention this very quickly. So I guess either people don't care as much as I thought they did, or there are not so many economists in the room, but usually we are skeptical of this kind of cardinal utility, I guess. So question is, if you give me a market with ordinal preferences of the agents over partners, when can we come up with a function that works the way U works, this function U works, and that is a problem that has been studied in different settings, and it's about the existence of a potential for this problem. So anyway, so we have a theorem that shows you when such an object exists, and there are some topological assumptions that are needed and some continuity assumptions that are needed of the ordinal preferences, which I'm not going to show you. But the main property that you need, so substantive property, is the acyclicity of this type of the preferences. So when you think that x and y must have the same objective, then if you fix x, you move from one partner of x, y prime. You fix y prime, you move from x to x prime, and then from x prime you move from y prime to y double prime, and so on. Each time improving in that agent's preferences. You shouldn't be able to form a cycle if there existed a potential. So that property ends up also being sufficient for the existence of a potential, as long as these additional, more technical assumptions are. Anyway, I'm out of time, and so I'm going to take questions and chat about it at the reception, which is next door, which Simon very kindly provides for us. So, I invite you all to have all the drinks.
So you're not in the branch yet?